Organic Chemistry Unit 5. Not 4, it is Unit 5, questions 17 to 21. So basically, in the blue booklet, there's only 3 organic chemistry units. The last one is unbelievably super easy. So the first one, the first 2 areas that come up frequently, R prime, R double prime, R triple prime thing, ACER has a fascination with it. There's not a lot of programs that ask those types of questions, so people are questioning with the GAMSAT. So we'll go over that and also look at some background information for organic chemistry. And then, of course, looking at a bit of stereochemistry. Stereochemistry happens to represent, among ACER's practice materials, there are 4 practice booklets, which of course you should own all 4 booklets, and you absolutely should be going over every single question in those booklets to make sure that you learn as much as possible from that experience. But those 4 booklets, if you look at all the organic chemistry questions, 40% of the organic chemistry questions deal with stereochemistry. So it doesn't mean that on March 22nd, 40% of your questions in organic chemistry will be on stereochemistry. There might only be a couple, there might be many more. You can't say. Every exam is different. But it's obvious that ACER is saying it's an important topic, judging from the way they've emphasized it. In recent, in the last couple of years, there's always been a few questions, but not as much as in their practice materials, but you should be prepared anyway, of course. So that is the plan. So the first thing is for you to go to Unit 5, questions 17 to 21. And today I'm going to use the video because I'm too slow with the whiteboard when it comes to organic chemistry. So it'll be faster if I use the video for this part. And today's video is brought to you by Gold Standard and Two-Door Echo 100% recycled pages. Okay, so I'm hoping that you have Unit 5, questions 17 to 21 open. I'm just going to give you a minute to look at it and look at some of the words being discussed, and then we'll do our thing. ACER has many problems among their practice materials and in their real exams that will use this R prime, R double prime, R triple prime to follow groups during a reaction. And so, and by the way, if you have a non-science background, don't worry. There's a lot of science students who will see this for the first time and still not know how to react to seeing this type of question style. So it is a matter of getting used to it and seeing it as often as possible. So first of all, in the first paragraph, I'm not suggesting that all the information in the first 2 paragraphs are really necessary to solve the problem, because it isn't. But it's useful to have a little bit of background knowledge, background information as to what they're talking about. First of all, they call these types of compounds beta-hydroxyacids. So the OH is on the beta carbon. Right, it's good, exactly, it's good that you're specific that it's the second carbon from the acid, because first of all, you see that it says beta-hydroxyacid. In organic chemistry, when we talk about organic acids, it refers to this functional group, which is the carboxylic acid functional group, because this is the most important organic acid. And so in this, whenever there's a carbonyl group, the second carbon is called the alpha carbon, and the next carbon next to it is the beta carbon. Now I want you to notice the irony of this. and that is that the functional group, carboxylic acid, is carbon 1, because this is the most important functional group that would be there for the organic chemical. And then the second carbon, so this is carbon 2, is named the alpha carbon. So alpha refers to the neighbor of carbon 1 or of the carboxylic acid. And the beta carbon, which beta would imply 2, but it's actually carbon number 3 is the beta carbon. So we have the carboxylic acid, and then on the beta carbon there is a hydroxy group. So this is the beta-hydroxy acid. Now, just in terms of some background information, what is it? Why are carboxylic acids so acidic? Okay, good. And what is the definition of an acid? Okay, so yes, this is the key thing, because you want to be sure that when they ask you questions, you don't get distracted by the different answer choices. So if they ask you, which is the strongest acid, right away you have to convert that question into which is the strongest proton donor. And good proton donors, sometimes you're able to just look at the molecule and know it's a great proton donor, like HCl, H2SO4, sulfuric acid, hydrochloric acid. But sometimes you're not quite sure, and you would have to look at the stability of the products. So in looking at the starting compound here, you look at the stability of the products, meaning if the proton is given off, will the resulting functional group be stable? So here we have what is called the carboxylate anion. So it's an anion, of course, and the carboxylate anion can engage in resonance. So you have these two equal structures. There's no reason why one should exist more than the other. And so you have these two equal structures that you can write, and that leads to a gain in resonance energy, which means more stability. Now, if you were to do a study on how many single bonds or how many double bonds there were in the carboxylate anion, how many would you find? Yes, you would find 0. And the reason is, when we say resonance, it doesn't mean that these two species are resonating between each other. They're not going back and forth. Neither exists in reality. What happens is that those extra electrons in the bond are delocalized between the two oxygens. And so essentially, it is like having a bond and a half, exactly. It's like having 1.5 bonds in between each of the two carbons and oxygens, because it is shared equally, evenly throughout. So it's that delocalization, without having one oxygen holding on to all the electrons, but rather delocalized between, that is what lends itself to added stability. So after saying all of this, are carboxylic acids strong acids or weak acids? Yes, they are among the strongest of organic acids, but they're very weak. But because they are so important, and the issue of resonance, it's important to keep this in mind. And of course, stability is also seen when the classic resonance structure of the benzene ring, in which you can see here, sort of in this little space left, you can see the two equal structures of the benzene ring. It is usually summarized by just putting a circle in between inside. And that summarizes the fact that the electrons in the double bond in the benzene ring is actually delocalized. And that's why the benzene ring is so incredibly stable and it's relatively difficult to react with, certainly far more difficult than just alkenes to react with. Okay, so that's just a little background about beta-hydroxyacids, where the name comes from, and the acidity of organic acids. So now let's get down to the meat. Now, notice in the section, there's a note that area. I want you to note that during the real exam, whenever you see note that, there are probably going to be some information that will help you solve the problem. So even in the first two paragraphs, for example, all that information is pretty useless. You know, figure 1 is important, but the first two paragraphs were not very helpful at all. But when they have note that, then we have to take special attention to it. Now, they say that the bromo compound must be an alpha-bromo alkyl or al ester, not an alpha-bromo carboxylic acid. And I know that that was a mouthful, but we have to just take a quick look at what is meant by that. So they're talking about the bromo compound. So we focus on the compound with bromine that is in the figure 1. And we see this. Okay, so this is an alpha bromo ester, they say, an alpha bromo ester. So let's try to remember what this means. So first of all, here is the carbonyl group. Okay, so this is the C double bonded to oxygen, C bonded to OR, and this is just the easy way to write it. So this is carbon number 1, but this is the neighbor carbon, and so this carbon is called the alpha carbon. So this is called an alpha bromo, and then ester. So the functional group of an ester is this. We put CH3 just so that I can get you to do a little nomenclature, and that. Okay, so the functional group of the ester is this part right here. Carbon double bonded to oxygen, oxygen, and R group. So this is the ester. Is everybody okay? Okay, good. This is the ester functional group. Can anybody name this ester? Right. So this would be methyl over here, methyl, and then you would name this part. So it would be methyl prop, 1, 2, 3 carbons, propanoate. Now, if you thought that was giving you problems, then if you're going to name an ester, just try to think of the carboxylic acid before you name it. Because what would you name this compound that I just drew? Exactly. So it's 1, 2, 3 carbons, so it's prop, and this is a carboxylic acid, so this is propanoic acid. So if you forget how to name the ester, just think of the ester as a carboxylic acid, name that first, propanoic acid, then it's easy for you to name whatever group is attached to it on this side. You'll never make the mistake of which side to name it. Okay, so that's methyl propanoic acid. Now, going back to the notes, it says that the bromo compound must be an alpha bromo alkyl or aryl ester, not an alpha bromo carboxylic acid. So the translation of that is that this R right here cannot be hydrogen. So you can see that if that R was hydrogen, we would have an alpha bromo carboxylic acid, COOH. But ACER is saying no matter what, R cannot be hydrogen. Just Okay, just by that one sentence, it will help you get two answers correct, number 17 and 18, because then you are going to be able to knock out things in 17 and 18 that refer to R as being possibly hydrogen, okay, because it cannot be a carboxylic acid. Okay, and then in the note that it says that R prime, R double prime, and R triple prime can each be any of hydrogen, alkyl, or an arrow group. But by the way, what is an arrow group? It says in the note that the second point is R prime, R double prime, R triple prime can each be any of hydrogen, an alkyl, or an arrow group. Right, so just like an alkyl group is an alkane minus one hydrogen, an arrow group is an aromatic hydrocarbon minus one hydrogen, and that's called an arrow group. So aromatic minus one hydrogen. Okay, so now that we have established R cannot be hydrogen, we're going to continue and look at some of the problems. So blood contains low levels of beta-hydroxyacidic acid. So in the back of our minds, we have an idea of what this looks like. It's an acid, it's a carboxylic acid, and it has beta-hydroxy, meaning there's an OH group on the third carbon. So these are just things in the back of the mind. But the more formal name, 3-hydroxybutanoic acid. Great. So we have the formal name, 3-hydroxybutanoic acid. So let's draw that out. So but is going to be 1, 2, 3, 4 carbons, and 3, put it here, in the third carbon, and the oic acid part, we have to add OOH. So COOH, 1, 2, 3-hydroxy butanoic acid. Next, I'm just gonna, I don't usually put in hydrogens, but I'm gonna put in hydrogens this time. Usually you wouldn't do it because of wasting time, but this is a special situation. And the reason is, look carefully at figure 1. I want you to notice something, is that if I were to draw carboxylic acid, I would really never on my own draw carboxylic acid with COOH on the far left side. For me, traditionally, you would draw the carboxylic acid functional group on the right side, traditionally, okay? But of course you can do it either way, it doesn't change anything. However, I'm talking to you about this because it's an issue of strategy. You do not have time. You don't have time to waste flipping things in your head, rewriting things, and so on. So when they tell me 3-hydroxybutanoic acid, knowing that ACER likes to do this R prime, R double prime thing, and you can see it on the paper, you see it's coming. If for me to have an easier time identifying the location of the different substituents, I'm going to draw everything exactly like ACER does. So that way it's going to be easier to identify what's going on. So that's the only reason why I did it this way, because I see in figure 1, that's the way they do it. Now, remember, R cannot be hydrogen. So now the question is to identify what R, R prime, R double prime, and R triple prime is. So right away, I know R can't be hydrogen, so I know that answer choices A and D are incorrect because they identify R as hydrogen. So now I can focus on answer choices B and C and identify what R prime, R double prime, and R triple prime are. So does everybody see that this position is can be identified as R prime in figure 1? Do you see it? That is R prime. That hydrogen is the spot where R prime is in figure 1. And then these two positions must be R double prime and R triple prime. Now notice our double prime and our triple prime are both attached to the end carbon. I don't know what the order is of these two compounds. I just know that they are both attached to the end carbon. So, what have I learned? R prime is equal to I hydrogen. R is going to be equal to some carbon group, okay, because this is an ester. So R is carbon. R prime is hydrogen because this is where it's located. Because every one field has to be hydrogen. If you're not sure, look at figure 1 and count the carbons from the COOH. And you'll see that on the second carbon is attached R prime. Well, this is the second carbon, so this is R prime. So we have R prime is hydrogen, R is a carbon. Then, among our double prime and our triple prime, one is going to be hydrogen and one is going to be carbon. Does anybody have a problem with that? So look carefully at this carbon is the carbon where OH is attached. Okay? So now look in figure 1 at the carbon where OH is attached. So you notice in figure 1, that carbon is attached to R double prime and R triple prime. Okay, so we know that that carbon is attached to one carbon to the left, one OH group on top, and R double prime and R triple prime. So this is why I'm saying that on our molecule, because this is the carbon with the OH, these two groups, I don't know which one is on top and which one's at the bottom, because this is not stoichiometry, this is not stereochemistry. It's not a Fisher projection, it's not a 3D model, so I don't know which one is on top and which one is bottom. But I know that both of these are attached to the 3-hydroxy carbon. And so our double prime and our triple prime are in that position. One is one and one is the other. Answer choice C. So moving on to question 18. Now the reaction sequence described would produce 3-hydroxypropanoic acid. So if you have some paper or pen next to you, please try to draw 3-hydroxypropanoic acid. Okay, so here's 1, 2, 3 hydroxy. Prop is 3 carbons, oic acid, carboxylic acid functional group. And as I said before, I would never normally draw the carboxylic acid functional group on the left side, but I'm doing it only because that's the way ACER has set up the problem. And of course they did that so you have to think backwards, or at least that you organize yourself so you don't have to think backwards. So there's 3-hydroxypropanoic acid. Does everyone recognize that this is going to be R prime? This is R double prime, and this is R triple prime. So everyone sees that? This is R prime, R double prime, R triple prime. So there you got it. And you know that R cannot be hydrogen. This is the second question that depends on the fact that you recognized that a carboxylic acid has hydrogen, and ester does not. It has an alkyl or an aryl group. They even underline that for you. So everyone sees that, and therefore, if those 3 are going to be hydrogen, just because you drew that out, then the R group is not hydrogen, then 18 is indeed, as you said, B. Yes, so it's B. But, you know, you see how as long as you draw it out the way ACER has it, then it simplifies it. And that's the purpose, is for us to see these strategies. So, next question 19. Please take a look at that and tell me what you think. I'm hoping that you notice this, that these compounds are called beta-hydroxyacids. Beta because it's on the beta carbon, meaning the third carbon. Beta-hydroxy carboxylic acids. So they all have the hydroxy group on the third carbon, always the third carbon. And because of that, the only answer choice that has a hydroxy group on the third carbon is that you're going to get an answer that fast on the GAMSAT, but you have to be open to the possibility that it happens. And so 19 is indeed B. Dave is asking, why is R methyl? Because R cannot be hydrogen, because in the note that area below figure 1, it says the bromo compound must be an alpha bromo alkyl or aryl ester. Ester, not an alpha carboxylic acid. Look at that bromo compound, which we drew over here. It means this R cannot be hydrogen. If it was hydrogen, it would be a carboxylic acid. But they specifically said they refused the possibility of a bromo carboxylic acid by saying that it has to be an ester. So it has to be an alkyl group or an aryl group. That is the reason why R is not hydrogen. We wouldn't know if it's CH3 or propyl. We wouldn't know, but we know it's definitely not hydrogen. So they wrote CH3. We accept CH3 because it would make an ester here. So let's look at question number 20. So I'm hoping everybody can at least draw this. This is ethyl 3-hydroxy-4-ethyl hexanoic acid. So it ends with hex. So the hex means 6 carbons in the longest chain. So we have 1, 2, 3, 4, 5, 6 carbons in the longest chain. It has oic acid. It means it's a carboxylic acid, COOH. So that's C, double bonded to oxygen, OH. And it has 3-hydroxy. So this is the first carbon because it's the carboxylic acid. So 1, 2, 3 hydroxy, which is consistent with the beta-hydroxy acids this whole thing is about. And it also says 4-ethyl. So 1, 2, 3 on the 4th carbon, there's an ethyl group, carbon, carbon. So that would be, I think, the most efficient way to draw. Now, looking at carefully, please look at the figure 1 and identify for me what's going to be R prime. What is R prime in this molecule here, 3-hydroxy-4-ethyl hexanoic acid? Yes. Yes. Just look at figure 1 carefully and count the carbons. You have COOH on the neighbor or the second carbon, R prime is attached. So COOH on the neighbor, the second carbon, R prime is attached. So here is R prime. So I'm hoping you're starting to see ACER is using R prime, R double prime, and R triple prime to follow things during the reaction. So it's just that. It's just to follow things during the reaction. Here's R double prime. And then also attached to the carbon in the hydroxy acid is R triple prime. So that means R triple prime must be this entire group here. That is R triple prime. So now, using this information, look back to figure 1 at the aldehyde or ketone. You'll see that the aldehyde or ketone is sort of drawn like this, which, by the way, I would never in my life draw an aldehyde or ketone like this. But there it is. Because normally when you see an aldehyde or a ketone drawn, you would draw the carbon, and that would be your ketone, with the carbonyl group up like that. But, to draw it off to the side, whatever. I'm doing it because ACER did it that way. So now we just have to insert this. The R double prime is down here, so I put it here, hydrogen. The R triple prime, I take this entire group and I plug it in there. So I pick it up exactly as you see it, and I'm plugging it in. Does everyone see that? You just picked it up and you stuck it in there. They told you where to put it. Now you only have to name it. So you name it by looking at the longest chain. And so 1, 2, 3, 4 carbons is the longest chain. And it ends in al. So it's butanal. And then on the 1, 2, second carbon, which would be the alpha carbon, so it's 2-ethyl-butanal. And the problem's over. It's answer A. Okay, so next, under the condition, blah, 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 the reaction between acetone and propyl bromoacetate would produce. So, acetone. So what's the first chemical called? Formaldehyde is correct. What is its systematic name? What is the systematic name of the first chemical here? It's definitely an aldehyde. No. Yes, methanal. Yeah. So meth means it has 1 carbon, and it's an aldehyde. So this compound is methanal. Okay, let's move to the second compound. What's its name? Yes, the systematic name is ethanal, but what is the common name for it? It's not ethanone. One means it's a ketone, and ethanone cannot possibly exist because the first of the ketones is acetone, which we'll talk about in a moment. So yes, acetaldehyde. So this compound, you could see it written as either ethanal, F for 2 carbons and it's an aldehyde, ethanal, or you can see it written as acetaldehyde. Okay, so this compound, what's it called? What's the systematic name for this compound? Propanone. That's correct. So, and you don't have to say 2-propanone because it's just propanone, because it could only be on the second carbon if it's a ketone with 3 carbons. So, what's this compound called in the bottom left? Ethanoic acid, but actually it's right. Ethanoic acid is the systematic way to name that compound, ethanoic acid, but that's not its IUPAC name. What? Can't end in all because all is an alcohol, and this has a carboxylic acid functional group. It's the most famous of the organic acids, yes. So it's acetic acid, yes. So that's acetic acid, which is ethanoic acid. And finally, what is this compound in the bottom right corner? Methyl ethanoate. is the systematic name. So methyl ethanoate, just like this is ethanoic acid, ethanoate. So methyl ethanoate is the systematic name, but guess what? That's not what it's usually called. And in fact, ACER did not call it ethanoate. So what is it? What is its common name? Not propanoate, because prop has 3 carbons. And there's not 3 carbons in a row. Whenever you use prop or eth or pent, it's because you have that many carbons bonded to each other, and it's the longest carbon chain. It's not ethyl acetate, but you're on the right track. That's right. It's methyl acetate. Just like this is acetic acid, so this is acetate. So methyl acetate. And that's why in this problem, question 21, they asked for the reaction between acetone, so they don't say propanone. This is a lesson to be learned. They said acetone, they didn't say propanone, and this is, from ACER's mouth, and then they said propylbromoacetate. Bromoacetate, so that means we have the acetate functional group. So these are 2 things to be sure that you're able to write, because if you can't draw these things, then it's, of course, it's difficult to solve the problem. So we're going to look at acetone and propylbromoacetate. So I'm going to, please try yourself on a piece of paper to draw propylbromoacetate. And, well, I know you know how to draw acetone, but you should try to draw it the way you see it in figure 1. That's the point. So I'm hoping you do something like what you see in front of you, because I'm just trying to draw it more or less like ACER did. So I'm looking at the alpha bromo ester, and so I drew the propyl part here, propyl, 1, 2, 3 carbons in a row, propyl bromo here, acetate, 2 carbons, just like acetic acid has 2 carbons. Acetate is the same thing as ethanoate. And so I have 2 carbons, and this carbon is double bonded to oxygen and bonded to the oxygen over there. Okay. So I'm hoping that everyone can recognize the position that this hydrogen is consistent with R prime. Do you see that? So look at figure 1 and identify in the alpha bromo ester that is the position of R prime. I'm hoping that you can also see, first of all, I would never in my life think to draw acetone like this, but I drew acetone like that only because ACER drew their aldehyde or ketone in the same way, and I want to be quick in terms of identifying things. So, yeah, you can use the bromine as a reference to which carbon has the R prime attached to it. Yes, you can use the bromine as a... So then for the ketone, I can see that this is going to be my R double prime, and this will be my R triple prime. So does everyone see that R double prime is methyl and R triple prime is also methyl? Okay, so once that's done, I'm just going to draw this a little smaller here so I can fit it on the same thing. But I'm looking at the molecule, the beta-hydroxyacid. So there's the beta-hydroxy acid that is on the far right of figure 1. Now I'm going to put in R prime, R double prime, and R triple prime. Now I've already said that R prime is hydrogen. So I put in the hydrogen, and I said that R double prime is carbon, it's a methyl group, and R triple prime is another carbon. So now it's just a matter of naming this. So the largest carbon chain, 1, 2, 3, 4. So it's butanoic acid, it's 3-hydroxybutanoic acid. There's also a methyl group on the third carbon. So yes, you're correct. The answer is D. Could you imagine? The question does not specify what acetone is anywhere. You just have to know that acetone refers to propanone. There's acetone, there's acetaldehyde, there's formaldehyde, there's acetic acid, there's acetate. There it is. That's not 100 different things that you would need to know. And knowing these ones are really, basic. Of course, benzene is IUPAC, so it's normal for you to know benzene.